Okay, here's our first set of notes on chemical equilibrium from chapter 15 of our textbook. In this section of notes, we'll talk about what chemical equilibrium is and how we define it and how reactions get to chemical equilibrium. And then we'll talk about the equilibrium expression and then how to calculate some quantities in the equilibrium expression. So the idea of equilibrium, so this basically happens when any reversible reaction, so something can go forwards or backwards, when everything happens, when they get to the point where they're proceeding at the same rate. So basically they're in some sort of balance. So it's important, a couple things that's important to note. One, that both the forward and reverse reactions are happening. All right, they're just happening at the same rate. So it's not that one reaction stops or that they both stop and you're all balanced. No, they're just happening so that they're canceling each other out and they're staying balanced. And then any reaction that's reversible will always go to equilibrium as long as the system is closed. All right, so that's important because if it were an open system, for let's say you're producing a gas, that gas can escape and you're never going to get your equilibrium concentration because you have to have that buildup of products to slow things down. So it has to be a closed system, and they're happening at the same rate, both forwards and backwards. And also, the amount of the reactant and product at the end will remain constant, though not necessarily equal. So you see that in this reaction here, we're starting out with all N2O4, and as that decreases in concentration, your NO2 is increasing until you get your equilibrium point. And now this is staying constant. They're not equal. The lines are not the same concentration at all, but they're flat because they're staying equal. So when we're showing something that's in equilibrium, again, both the forward and the reverse reactions are happening. So when we do this, instead of just writing a single arrow, we always write it with a double arrow. So you know that's a reversible. It can go this way, or it can go back the other way. And then the equilibrium constant. So this is very similar to your reaction constant, your kinetic constant K, in that they're derived basically the same way. So if we were to think of this example we've been doing here, the forward reaction of N2O4 decomposing to two NO2s. If we were to look at that, we would say, okay, our rate law for that is our constant Kf for forward, concentration of N2O4. It's a single order because we have just one there. And then we have a reverse reaction, same thing the other way, two NO2s decomposing back to, or coming together, not decomposing, to N2O4. And now this rate is the reverse K in NO2 squared. So if we were to put everything together, setting them equal to each other, you get this, where K forward over Kr equals your NO2 squared over N2O4. And since the ratio of the rate constants is constant at that temperature, we can write it like this. So instead of just saying Kf over Kr, we can call that Keq. So it's our equilibrium expression. Sometimes you'll see Kc for K concentration. So like in this case, you would see concentration. Or if you're working with a gas, instead of concentration, you have partial pressure. So you might see Kp for pressure. So in a generalized reaction, A with A moles, B would be moles, yada, 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 the overall equilibrium expression would become this. So your products go up on top, right, and you're raised to the stoichiometric coefficient for those, and same thing for the reactants would then be on the bottom. So that's your generalized form. Products on top, reactants on the bottom. And again, since pressure is basically the same thing as concentration, they're proportional in a closed system, you can do the exact same thing with partial pressures. So this is Kp, and you got the pressure of gas C at that whatever stoichiometric coefficient. So things that are handy to know, you're not going to have to worry about converting between Kp and Kc. There is some of that stuff in your book, but that's beyond the scope of our class. Keq is dimensionless. We talk about it in terms of pressure or concentration a lot, but in reality, we're talking about how this works, it's in an ideal solution or an ideal gas, and we talk about the activity, which is the concentration relative to your ideal solution, which is usually a 1 molar solution. So if you had, 2 molar solution relative to your 1 molar solution, you end up getting a 2, right? Because the molars cancel out. So no dimensions, don't worry about that. And just like your little k from last unit, Keq is specific to the reaction and at that certain temperature. That's why you always see a temperature listed in the problems. It's also important to know that equilibrium can be reached from either direction. It doesn't matter if you start with, in this case, the N2. Right? We have N2, we have H2, and they're coming together, and initially we have 0 NH3, and we're forming NH3, or you can go the other way, because this is a reversible reaction. You could have 0 of H2N2, all we have is NH3, and that's going to decompose. Either way, it goes to the same endpoint. You can see, obviously, again, they're constant, but not equal, but the forward is the same as the backwards. Right? Those amounts are equal, so you get to the same equilibrium point. And when you see value k, what does this mean? This is handy to know. So if your k is a lot bigger than 1, then we would say this reaction is product favored. And if you think about this again, because you've got in your expression, you've got concentration of products over concentration of reactants. So if it's a large number, that means you would have to, or a large positive number, you would have to have a larger amount of products. So this means that the products predominate in this equilibrium, and we would say that if k is much greater than 1, equilibrium, we say, lies to the right. Right? It's on the right side of your expression. The reverse is true. If k is much less than 1, the reaction is now reactant favored. So again, if you're thinking about your fraction, maybe it's like 1 over 250 or something like that. So you've got a lot more reactants in that case. So the reactants predominate, and so this equilibrium lies to the left. So you'll see these terms a lot: lies to the left, or goes to the left, lies to the right, or goes to the right throughout this unit. And how can we manipulate these equilibrium constants? Well, if we take our forward reaction and we get this to be our Kc, if we wanted to do the reverse reaction, it would just be the reciprocal. So 1 over 0.212 is 4.72, so it's just the inverse of that. And then if we wanted to manipulate the stoichiometric ratios, we can do that. Right? If we wanted to double everything, 2 N2O4 as opposed to 1, 4 NO2s instead of 2, we would just take our Kc and raise it to that power. So we doubled it here, so we're going to raise it to the second power. If we tripled, we would cube it, and so on and so forth. Finally, if we were going to figure out a net reaction, if all we had was the individual steps, well, the k of the net reaction is just the product of the intermediate steps. So k1 times k2 equals k for the whole reaction. So far, we've been talking about homogeneous equilibrium, so everything being in the same state. When things are in different states, it's a little bit different. So if we're talking about solids and liquids, if we think of the concentrations of solids and liquids, you can figure those guys out by multiplying the density times its molar mass, which basically means it's constant. If we were to double the amount of solid, its volume would also double, and it's always going to be that way, that proportional amount. So since that's the case, we don't really need to worry about them in our equilibrium expression. So in this case, we've got PbCl solid, Cl2 solid, and we've got an aqueous solution of lead ions and aqueous solution of chloride ions. That's all we care about in our equilibrium expression. This doesn't matter as far as figuring out your Kc. So for example, how would you do these, right? Your job is to figure out the equilibrium expression. If we look at them, what do we get rid of, right? Gas, keep that, gas, keep that, gas, keep that. Liquid, we don't care about H2O. So now we know what our expression is. It's just going to be the concentration of CO over the concentration of H2 times the concentration of CO2. All of them are no coefficients or a coefficient of 1, so they're raised to the 1. Go down here, this one, solid, oh, we don't care. Gas, yep, keep that. Solid, get rid of that. Gas, keep that. Okay, so now our Kc is going to be concentration of CO2 squared over concentration of CO squared. So that's how to figure out or to write your equilibrium expressions. A couple other examples. Think about what's going to happen. So this is just about thinking about what's in the reaction. Does the reaction need everything that it needs? So we've got these things, a couple different conditions here. They're in a closed container, and this is the equilibrium we're working with. This is our reaction. Calcium carbonate solid going to calcium oxide and carbon dioxide. So if all we had was calcium carbonate, could we get to equilibrium that way? It turns out, yes, we can, because that's just going to decompose until you get enough of these that they're going to start recombining to each other and coming back to calcium carbonate until it becomes balanced. You get to equilibrium. But yes, this side of the reaction has everything it needs, so it's going to work. How about if you have CaO and CO2? Okay, well, those are both the parts that you need on the the product side, so it's just the reverse reaction. So yeah, those guys are going to combine until you get to equilibrium. How about if we have calcium carbonate and CO2? Now we're dealing with things on either side of our equilibrium arrows. In this case, we have a lot more CO2, greater than the Kp, so the equilibrium pressure that we need. So we've got lots of CO2. So in this case, no, we're not going to get to equilibrium because we don't have that calcium oxide, the solid, for this to react with to go back this way. And then what if we're going to do calcium carbonate plus calcium oxide? All right, calcium carbonate plus calcium oxide. At first, it seems like this might not work because you're on separate sides, but basically this is the same thing as A. Right? As this guy decomposes, it's going to create these two things, and then they'll react with each other. The difference between the last situation is there's not as much of this. Before, we had lots of CO2, and so this is generating at basically the same rate, the same amounts that you need, versus the other one, there was so much more carbon dioxide that it wouldn't ever get the proper ratios that it needed. All right, so most often you're going to be asked to figure out what your equilibrium expression is, or what your K value is. And so if we know all the equilibrium concentrations, then it's easy. All you do is plug it in, right? And you've got your K. Usually, though, they're not going to make it that easy on you. So if you don't know the equilibrium concentrations or the pressures if you're dealing with gas, we create what's called an ice chart. So let's see that example at work. So here we have a closed system that initially contains 1 molar H2, 2 molar I2 at 448 degrees Celsius, and it's allowed to reach equilibrium. So we're in a closed system, so that's all good. Analysis of the equilibrium mixture shows that the concentration of HI, our product, is 0.5 molar. Calculate Kc at 448 for the reaction taking place. And here's our reaction down here. So we're going to create the ice chart. So that is this right here. What do we know? So the ICE stands for I is for initial, or initially we have, C for change, and E for equilibrium. And then I've written my reaction up here, and I tried to line everything up so it sort of makes sense to us, because that will become important. So initially we know from our problem that we have 1.000 molar, 2.00 molar, and initially we don't have any of this, right? This started out without it. And when we're all done, we know that we have this much of the HI. And so what can we tell from this? Well, we can very easily see that we started off with 0, and now we have 0.5, so therefore our change obviously was 0.50. And based on stoichiometry, we can figure out these amounts here. Since these each have a coefficient of 1, this has a 2, it's half as much. So now we've got these guys decreased by 0.25, just half of this. 1 is half of 2. So each of them decreasing by 0.25, then this one increasing by 0.5. Now that we have our change, we can very easily figure out our equilibrium concentrations, and that's all we really need, because now we have our equilibrium expression, and we just plug those values in. Concentration of HI squared, right there. Concentration of H2 squared, 0.75, not squared, H2, 0.75, I2, 1.75, multiply it all out, 0.19 is your Kc. And again, that is unitless. And that's all for today.